Hey math kids, today we're going to talk about rates of change. And, we've seen in previous videos the derivative can be written like this. And if you notice, it looks very similar to our definition for slope, which is a rate of change, right? Change in y, change in x. This is change in y, change in x, but it's when it's an infinitely small change in y and change in x. And so we're going to go through this story problem. It says, according to a psychologist, the ability of a child to understand spatial concepts is given by this equation, where t is years, and it's defined for 5 to 18. Okay? It says, find the rate of improvement in the ability to understand spatial concepts when a child is 9 years old and then 16 years old. Okay, so we'll just start right there. This has multiple parts. Okay, so what we know is we want to first take the derivative of the function that we're given. So I'm going to rewrite it as 1/3 t to the 1/2. And then if I take the derivative, so we'll just call it dA, we're going to still have that 1/3 out in front. We're going to bring the 1/2 down, and then t, and then we reduce it by 1, so it becomes negative 1/2. So if we simplify that, it's going to be 1/6, and then this is the square root of t, but it's on the bottom this time. Okay, so this is our derivative that we're going to use, and that's what we're going to plug 9 into. And so if we plug in 9, we get 1/6 square root of 9, 1/6 times 3, which is 1/18. Okay, so the answer to this one is 1/18. And then if we plug in 16, we get 1/6 square root of 16, 1/6 times 4, so that gives us 1/24. Okay, so what that's telling us is the amount that it's changing of like understanding new concepts. So even though we know more when we're 16 years old, the difference that we changed from like 15 to 16, or even just instantly, from like 16 in 1 day to 16 in 2 days, is much less. It's 1/24 than when we were in the same situation at 9 years old. So like 9 years old in 1 day, 9 years old in 2 days, we understood spatial concepts. We understood it more, like the change in what we knew was larger, even though when we're 16 we actually know more. So this is about the change, not necessarily how much we know. Okay, B. Now it says show that dA dt is greater than 0 when we're on this range right here. Okay, so this is dA dt, and we want to basically prove that it has to always be greater than 0. Now, we don't need to like really go through math or anything to do that. We're just going to reason through it. Now, the square root of t is the only thing that's changing. So all the stuff on the outside is positive. And then this has to be positive because anything under a square root can only give us a positive outcome. And so if we do positive times positive or positive divided by positive, however you want to think of it, this has to be positive. Now the significance of that means, because remember, it's how much we're understanding. We're always understanding more because it's positive. Our change is positive, so we're always understanding spatial concepts more as long as we're in between 5 and 18 years old. So that's basically all that says. Okay, now it says the second derivative is always less than 0 on the same range of values. So for this, we would want to take the second derivative. So I'm going to kind of look here, but it's going to be 1 over 6 t to the negative 1/2. That's our derivative. And so if I bring that down, I get 1/6 times negative 1/2. And then t is raised to the negative 3/2. So if I simplify that a little bit, it's going to be negative 1 over 12. And then I'm going to get the, no, not that. I'm going to get square root of t cubed. All right, so we're going to reason through this. So here's second derivative, and we want to know why it's always less than 0. Well, this piece is always negative. This piece, because it's under a square root, is always positive. So negative times positive is always negative. And so it's like that. Now, in the context of the problem, the significance is that the amount that we're learning, so remember, we have the amount we know, that's our original function. Then we have the amount that we're learning, and that's our derivative. And the second derivative is the amount of stuff we're learning. So it's, or like the amount that our learning is changing. That's what I mean for the second derivative. And so we can see that just right here, when we were 9 years old, our rate of change was 1/18. And then our rate of change was 1 over 24 when we got older. And so that amount that we're learning is smaller. And so the rate of our rate is going down always. We're learning less and less and less from each time period. Hopefully that made sense. Specifically in your book, I'm just going to read their answer because it might be more straightforward. This means that while the ability to understand spatial concepts increases with age, once again, that was our first derivative, the rate of increase slows down with age. Okay? And let's move on to the next example. Okay, it says the cost in dollars of producing X items in a factory each day is given by this, C of X. Okay, and then part A says the derivative is called the marginal cost function, and they want us to find it. Okay, so the constant goes away when we do the derivative. 12x becomes 12, and then we bring down 0.8 times 8, so it's going to be 0.64x, and then we reduce that by, whoops, that's wrong, decimal error. So that's going to be 6.4x. And then when we reduce that by 1, it's going to be negative 0.2. Okay? And that's the first thing they ask us to find. The next thing is find the marginal cost when there's 150 items and interpret the results. Okay, so all we have to do is plug in 150. Okay, open up my calculator. So we have 12 plus 6.4 times 150 raised to the negative 0.2. Okay, so we got 14.35. Okay. And now, they want us to find this, and they want us to compare the answer. Okay. So what we're going to do is plug in 151 to this, get a number, plug in 150 for all the x's here, get a number. So I'm not going to actually do it, but I'll show you like what I'm doing, and then I'll just tell you what the answers are. Okay, so if I plug that in, I end up getting that. So that's my C151. Okay, and then if I plug in that, I get my C150 is equal to that. Once again, just use a calculator. Okay, now if I take this thing minus this thing, or this thing minus this thing, I end up with 1435. Okay, so those are two ways to look at it. And what it is it's the actual cost to jump up from making 150 products to 151 products. So we decide, is it worth it to make one more product? And that's it on that one. Okay, Kathy is using a compass to draw a circle. The arm with the needle is 8 centimeters long, and the arm with the pencil is 9 centimeters. So this is needle, this is pencil. Okay, the angle between the arm is theta. Okay, write the radius of the circle to be drawn in terms of theta. Okay, so what we're going to do, we're going to use the cosine rule, if you remember that. And so the cosine rule is, here, let me draw a diagram actually. This will be helpful. So we basically have a triangle. We have this, which is the radius of the circle. This is 8 centimeters if it's the needle, and this is 9 centimeters. And then we have theta right here. Okay. So opposite sides are what we use for our c. So we have c squared equals a squared plus b squared minus 2ab cosine theta. So when we do that, the r and the theta need to be the c's. Oh, this is typically c. Okay, so we're going to say r squared equals 9 squared plus 8 squared minus 2 times 9 times 8 times cosine theta. Okay, and if we simplify all of that and solve for r, we're going to get r is equal to the square root of 145 minus 144 cosine theta. Okay, so all I did was multiply these to 144, square, square, and then add those together, and it gives us 145. And then I square rooted both sides, so it looked like that. Okay. Now, to make it easier, what we're going to do is take the derivative of r, because we want to know the rate of change of how the angle is changing on this next part. So it says, hence, find the rate of change in r with respect to theta when theta equals 60. So we want to, in other words, we just want to take, anytime we hear that phrase, rate of change, and we're in a calculus situation, we're going to take the derivative. So I'm going to just rewrite this as 145 minus 144 cosine theta raised to the 1/2. Okay, now when we take the derivative, we bring down the 1/2, rewrite the inside, reduce the exponent by 1, and then we have to multiply by the derivative of the inside. The 145 will just go away. We'll get negative 144 times negative sine theta. Okay, and when we simplify that, we're going to, the negatives will cancel, and then 144 cut in half is 72. And we're going to write this as a fraction. So we used up that, and it's 72. All of this goes on top of the fraction, 72 sine theta. And then this is a negative exponent, so it's going to be a square root, and then 145 minus 144 cosine theta. Okay, and they gave us a specific angle to test out. And so they wanted us to plug in let's see, what was it? 60 degrees. So if we plug in 60 degrees, we go 72 sine 60 degrees over 145 minus 144 cosine 60 degrees. If we just simplify that, let's see. Let's just go through and see what we get with that. Okay, so I'm going to go piece by piece. So I'm just going to say, whoops, I got to go to mode, change it to degrees. Okay, so if we do sine 60, it's going to give us 0.866. So let's see. So I'm going to bring this up here. So I have 72 times 0.866. Okay. Then I have 145 minus 144. And then I need to find cosine 60. And that's 0.5. Okay, 0.5. And then if we just plug in the rest of it, we're going to do like 72 times 0.866. And then we divide that by square root of 145 minus 144 times 0.5. Okay, and then we get 7.3 on that one. 30. Okay, and that's everything for that section. If you need additional help, come to Math Lab. Until then, calculator.